Today we're just going to look at the design of connections. So if I just have a quick look here into my product range and into steel design, and then we will see we have our moment and simple connections. In here we can see that it works, yes, as a totally standalone program, but it also works fully integrated into the master frame and in the master port. That helps to reduce input errors and data errors. There is also a mini version of this moment and simple connections programs inside the PowerPad. Now, one of the most popular questions I get asked is, well, what sort of connections can we do? And just before we go into the use of the software, I'll just pop up this little diagram that shows you we can do eaves type connections, apexes, base plates, beam splices, column splices, beam simple connections, flexible end plates, fin plates, angle cleats, and the same with the columns. So let's go and use the software and we'll just review these different types of connections. So it's going to be 4 stages today. We're going to first of all view and review the types of connections that can be done using the MasterSeries, and then we'll design a few joints manually to show you how easy and fast and flexible it is for designing joints. And then thirdly, we'll look at the use of the linked design. For those of you who have our frame analysis or portal frames, the job's even easier because you can just pull the data straight in from there. And then finally, we'll do a review and we will look at the differences between the Eurocode and the previous BS design. So let's start the MasterSeries. I should say that I am broadcasting today to over 20 countries. I know I have people coming in from as far afield as Mexico and the USA, to the west of me, and the Seychelles and Korea and the Philippines, India, Malaysia, Malta, all over to the right, who are staying up late to see me talk. Okay, front screen of the MasterSeries, very simple, very straightforward. I'm using version 2014-08, August 2014. I'm also using a 64-bit version. With connections, that's not a big problem, but if it was finite elements and dynamic analysis and stuff like that, yes, that's what you want to be using. So, without any further talk, let's just go straight into connections. And I'm going to go to my recent files, and let's look at this joints demo file that I've prepared for you. You can see we can review it before we select it. We can select other files and we can use short and long file names. But I'm just going to get this file and have a quick review. So first of all, we have our standard connection. We have our standard eaves type portal frame connection. Bolts, end plates, welds. And the nice thing is that we can easily modify these things. If I wanted to remove that row of bolts, I just go to my bolts tab and I just say I don't want that row of bolts, and everything suddenly updates. That updates, the results updates. If I take out another row of bolts, that updates, and in this case it was just a graphical thing, but with one row of bolts top, it's now failing. I know it's failing because it's all gone blue down below, but we'll look at that in detail when we're doing some design. Let's move through the different connections. I have 21 connections here, different typical connections. This is the same with an extended end plate. In this case, the weld is not happy. So we've got our blue and we've got our weld, but we're not in the design process yet. So we'll just move on. And we're now into a extended end plate. Yes, we can do more than one row of bolts above and below. We can actually do up to 3 rows of bolts above if you ever really want to do it. The only requirement is that if there's more than 1 row of bolts above the top flange, it needs to be stiffened. And likewise on the bottom. So we could do quite enormous stiffened gusset connections. Moving forward, we then move into our typical apex connection. And the apex can be either this type of haunched apex standard, or it could even be your more standard simple connection. If I came along here very quickly and just said, there we go, no haunch, no slope, it's just a beam to beam connection as a M-plated splice. Moving forward, we then come into our base plates, axial, or in this case we do have a moment. We can see our moment because our compression area is offset to one side. I will add that we're all doing this to the Eurocode as we advertised. We're also designing, and I should actually say no, we're not. We're now doing it to Eurocode. I apologize. We can switch between codes. So now we're designing to the Eurocode 3. And we're using the UK National Annex. Now at the end of this seminar, I will hopefully go back and show you, if I remember, how to change your national annexes. You can, under your standard design options, choose what annexes you have. I have the UK, Ireland, the Euro norm, and I have created an additional one of the UK with a bit of a modification factor, which is really sometimes used in analysis of frames rather than anything. So I'll stick with the UK. So the UK National Annex, and we can see that we're also working to publication P398. This is the big SCI publication on moment connections that took quite a long time to come out, and thus the delay in everybody releasing full moment connections to the Eurocode. As well as having this little brief summary and blue-green screens top and bottom, we can at any stage scroll down and look at all the detailed results, and we will go over those again when we're looking at the different problems that and differences between the Eurocode and the BS. So that's our simple slab base plate with a bit of moment, no tension in the bolts yet. If we wanted to, we could put in a bigger moment, and we now get a tension in the bolts, and we get a problem with our compression capacity, so we need to strengthen our concrete to solve that. So we're getting too much there. But again, as I said earlier, we're going to do that later. And then also we have the same for the hollow sections, be they circular or rectangular hollow sections. For the circular hollow sections, we can even put the bolts on a pitch circle diameter for you and give you a circular compression area and a circular cantilevers out from the flange. And then we have the stiffened base plate. So we're still only on our third principal connection, and this is our base plate with stiffening. We have quite a few different configurations of stiffeners, and if I just moved over to the stiffeners, I can ask for one coming out of the web, so extending the web. In this case isn't going to help us. If I click again, we can have two across the toes as we saw. We can have toes plus the web. We can have the extending flanges. So that's going right across the flanges, making those flanges wider and giving us a wider area to bend against. Again, in this case, it's still not very, very happy. And we can go all the way up to having stiffeners sticking out everywhere. And very, very complex to build, very expensive to build. Obviously, when you have a lot of bolts and tension, that's probably the type of thing you might want to go for. But personally, these days, we find it a lot more economical to just put a thicker base plate in the first place. So that's your base plates. And now we're moving into the fourth type, the beam splice. The beam splice, very straightforward. Top and bottom plates, and different number of bolts top and bottom, web plate. We can also have internal bolt plates, and as you should notice there, we also have countersunk bolts. We could do the countersinking if we went back. We can countersink very easily. Flange plates, I wish to have them countersunk. And our capacities should just change ever so slightly due to the countersinking, because it will make allowance for those. And then we also were able to do complex staggered. So this is staggered in pairs. So outer, inner, outer, inner. But we also have, and very useful in very narrow flanges, is two bolts alternately staggered. And all that means is we get a better net area for tension, because when you have a very narrow flange, a 133 or 102, putting two 20mm bolts in 22 holes is going to take out 44mm out of your precious 102, which is very, very expensive. So instead you can stagger these and spread them out so that at any one point it's only one, or with the staggering calculation, maybe 1.2 bolts taken out. Very, very useful. We now move into the column splice, and we're looking here at the standard column splice, non-bearing cover plates. Very straightforward. We can do obviously column splices that have a different thickness or different section size above and below. In this case we've countersunk the bolts again to keep it nice and clean. We've gone for division plates so we can see and confirm our spread of bearing between them, with angle cleat attachments at the web. And finally we can, in the column splice, do cap and base plate connections. Not ideal for doing colossal moments, but for small moments and axial loads, perfectly fine. And now we want to move into the hollow section splice. The rectangular and square hollow sections, you can define top, bottom, left and right bolts. You can actually in this connection define torsion and everything. You have shear in two directions, moment in two directions, and a torque. So all 6 degrees of freedom, or all 6 restraint directions, are resisted. And then your circular hollow section splice. Very straightforward there. Now finally, and very, very quickly, we'll move into the simple connections. Now the simple connections to Eurocode have been out for quite a while, because that publication was produced about 1.5 years, 2 years ago. That is the P358 rather than the 398. The 358's been out for quite a while. In this case we're looking at a plate girder. We've built up a section that's about 1200 deep, and in one case we've got a single notch, in the other side we've got double notch, and we're designing that for you. Plate girders are dead easy. Just choose a section and just put in the values and go. If you wanted to, in this left hand side, we want to say, well actually we don't want to use a built up, we're just going to go for a 1016 by 305 section. It will then pop in that section and start to design. Now it's gone blue in the top because now with our bolt configurations, this bolt is hitting this flange, and we would need to make preparation to remove that or reduce the number of bolts on the other side. I will not fix that at this moment in time. And then the second type of simple connection is your most popular one these days, your fin plate. And we can handle both single rows and double rows, or in this case a double row with the bolts alternately staggered. We also do the two forms where you can have a rigid support or a flexible support, and that's quite useful so that you can the default is to assume that this is just a shear load in the web and the weld, and therefore you have a torsional moment on these bolts, which puts a lot of load on the bolts. Whereas if you assume a rigid support, you have shear and moment on the weld and just pure shear on the bolts, and that reduces the additional loading due to torsion, which does now no longer exist theoretically on those bolts. Both methods are valid to the Eurocode, and we cover both. And then finally you have the angle cleat. The angle cleat's quite strange in that in the Eurocode they've actually left it out. But there's no reason why we can't design the angle cleat using the rules and methods of the flexible and the fin plate together, and that's what we've done. We have given you this angle cleat. And then of course we can do the same connections with columns. In this case this is a column connection rather than a beam. And the nice thing I think about the column connections, and I think the previous one it was a column connection as well, for the fin plate is we can notch our connections. So if I was to go to my web and I was to say that my column section in the one side wasn't a 152 wide, but let's go way up to a 191, and then we looked at the column, we'll see that it actually notches in that flange so that it fits. We've also, because of this line, taken out the bottom flange so that we can present that beam down the middle of the column web and drop it into place. Otherwise, if we didn't take this out, the fin plate would be hitting it. For those who want to be safe and give the fabricator the option of going either way, we can elect to not just drop both bottom flange but both flanges, and we say apply and close, and therefore we lose this totally in this side so that we're give the erector full scope to present his beam up to the fin plate in either direction. So that is in essence the typical joints that we do. So let's go and design a joint. Let's create a new joint. I'm going to go for a beam to column flange. Okay. And first of all, I'm going to set some physical sizes. Column size 610, but we'll go for an S355. Beam size, I'm happy, but I'll go for the 355 these days and say OK. I'll now make it such that it is 900 deep and 1500 long, and I'm going to give it a slope of 12 degrees. So I just want that actually to face the other direction so that it looks the way it is on my calculation. So this is the connection I'm going to design. Let's put some values on it. I'm going to give it a 500 kilonewton meter moment, and I'm going to give it a shear of 350 and an axial of 1 or 240. I'm going to say the column shear pre-existing is nothing because we're just in a portal frame, and the haunch at the moment, the end of haunch moment, is 300. So looking at it now, we have, as we can see, a blue background. We've got failures. We're failing by 2.25%. So the first thing I would do would be to add more bolts very quickly. Give me another row at 90. So we're now down to only 49% overstressed. Very quickly we're getting there, but we can see from here that it's no longer the bolts that's the problem, it is the compression. So we come in and we will add in a bottom stiffener, and we'll put a 12mm stiffener. So we've now dropped back down and we're now only 34% overstressed. Let's add another row of bolts and make that 90. So bolts are happy, shear capacity is not. We can either add another row here and let them be used in shear, or more correctly put another row down here. So I'm going to go for my bottom group and put another row 90 up, and my connection very quickly now works. I can also come along and add in a second loading case. Go back to my forces and I'm going to put in a negative 267 with a axial tension of 110 and a shear of, doesn't really matter the direction, but I'll put it in negative, of 200. Maybe that axial is not enough, but we're seeing that it actually works in reversal because we already had that additional bolt in the bottom being available to us. Let's put that up a bit. And we'll see now that it would work if we had a compression stiffener in the top this time. So plates, putting in a top stiffener at 10 mil, and it now works. But what about case 1? Because we've modified things, case 1 may not work now. So we can go back manually and look at it and find it does work, or we can just say scan for failures and it says, yep, there's no problems with that joint. If there was a problem, it would have stopped. So if I come along, take that top stiffener out, and I don't know about it because I'm looking at case 1, but I now say scan for failures, it'll go to case 2 and stop saying, come on guys, fix this, we've got a problem. And we put that in. And we can have up to 10 loading cases. Normally 2 will do. Now, if I reset everything back to 0, first of all, close that, reset, yes. We're back to our basic joint. I'll just give it a few starting points. I'll make this 90, and then I'll say auto design. So instead of us manually doing it, we can ask the program to try 90 centers and go and design it for all the different loading cases, and you can see as it did the second case it eventually popped in that top stiffener and it's got the same answer as me. Now the last thing I want to look at in this joint before we review the joint is the welds. It will by default have put in just 6 mil and basic welds. Now we don't need to have such big welds. We can put a smaller weld in. We could put a 10 mil weld in there, and we'll put a 6 mil weld in up there. So we've reduced our weld sizes, and 6 mil welds here and here are sufficient for this connection. Quite reassuring. If we wanted to, and I'm just going to push this out a wee bit so we can see it. This 6 mil weld, if we were into a large weld, say a 15 mil weld, that's a very large weld to lay down. Now both the BS and the Eurocode allow you to do something called deep penetration, where you're welding with such good quality welding materials and welders that you're able to guarantee that you'll get 3, 4, 5 mil of interpenetration between the plates to give you an extra weld. So you could say put down a 10 mil with a 5 mil deep penetration. So it's limiting it to 4 mil maximum deep penetration, and so it's giving us a 14 mil weld there. So we have facilities like that. So that's how easy it is to design a connection. That's how quick and easy it is. If I was to take a beam splice, add myself in a beam splice, and say OK, I can now say, well, section 33, well, I'm happy with that. Now the moment capacity is 400 and the shear is 600 and the axial is 2300 of my section. So I'm going to turn around and put in a moment in MX of say 250. Alarm bells, ding, 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 ding. Things are problematic. And a shear of 100 and an axial of 400. So what I need to do is to come down and look at my problems in reality. So clearly it's the bolt and shear. We could possibly thicken up because we're looking at, it's the ultimate, it's the problematic one, giving us 94 ultimate area. So it's no good looking at the bearing of these. The bolt itself is the problematic area. So we need more bolts. Very, very simple. And one of the nice things we've got in the program is this ability to use something called auto change. And auto change saves you typing. So if I go to flange plates I can turn around and say, give me 3 rows of bolts. Hey, it's happy. Top. Now the bottom doesn't need as much because it was in compression and therefore have been cancelled out. Half compression plus the tension gives us a smaller value. My next problem is my web plates, and we're way up here in our design. Our shear of this plate is not very healthy. So what do we need to do? We need to get possibly some thicker plates and some more bolts. So let's go to web and we will see whether or not putting in another row of bolts. Another row of bolts does help. It's bringing those values down. So that is a solution. It's a big problem. Let's see if there's another solution. We're only at 13% overstressed here. Maybe if we lengthened the bolts up, we would get the lever arms we want, but now our bolts are too close together. So coming back to 95, let's increase the thickness to 8 to 10 mil. So that's solving everything but this problem with the physical bolt. The plates are now okay, but the bolts themselves are not happy. We could possibly go for a different type of bolt or larger diameter. So we could come back and we could say, let's look at our bolt types. Well, we're using 8.8s. 8.8s are not necessarily the best to be using in these environments because your whole joint can slip, and if we looked, actually there would be a warning to tell us in our dimensions that we should really use either close tolerance holes or high strength friction grips. So I'm going to go for tension control bolts. Oh yeah, they're not necessarily as good as one thinks. We're going to need more bolts. Sorry about that. Would 22s help? It'll help in some places. Let's see, 24s in, 24 mil bolts. We're obviously going to need another row of bolts there, but I suspect we're going to need that additional row of bolts in the web still. And that makes it work. So my forces were quite high in places, so yes, we are going to need a lot. Now, we possibly could have reduced the overhead here by trying to stagger these bolts, pull their centers down, say about 65 by 70, 65, and then we go up and then go out and out and out. So it's probably 2 or 3 bolts less in total to make that work with staggered bolts. Possibly pulling that in, extending that up and up. There we go. By giving it a bit of more vertical lever arm, we've got away with fewer bolts in the web. You can actually also in certain instances go for only one web plate, but not necessarily a wise thing always. So that is a couple of joints designed, a beam splice and a moment connection, all very, very simple. The second way that we use this program is in what we call linked design, integrating with our frames, our portal frames, our multi-story structures, our industrial buildings, whatever you want. Recent files, my joint demo is a pretty strange structure, but I thought it was quite nice, so I chose this to load. So this is my little frame. I'm not going to claim that it's perfectly designed because it's not. Some of the section sizes are all different down here just for our demonstration purposes. Some of the loading is just for our demonstration purposes. Just excuse me a second. I have a little application here that seems to be popping in and out. I'm just going to get rid of that. There it goes. We won't have that interrupting us anymore. Sorry about that. So let's analyze it. 90 loading cases as a space frame very quickly. It's going to take about half a minute, less. It's 25, 30, 40 cases. It's telling me that down here at the bottom if you're keeping track. 60 cases, 70, 80, 90 coming up in a second or two. So that's a frame reanalyzed just to make sure everything's correct. Now the yellow sections for your information are composite beams, and the green ones are our normal structural steel. So design, connection design. So I have already set up some connections for us. So if we look at our frame, we'll see that this is a haunch. And again, if I reset that back to nothing, we'll find it's failing and failing. I can now come in and say auto design, and it will design that connection for us for all loading cases, in this case all 90 loading cases, very quickly, doing a double pass to confirm everything's okay, and then we can sort this bit out manually afterwards, and it's nearly done everything for us. And I can see the only problem is the clash coming in tight. It's telling us that this bolt may not be accessible. Now there's two ways of solving that. One way is to come in to options and tell it in eaves and apex to draw the nut the other way around, and then there's no problem because the bolt's been presented from this side with the nut coming in from this side, and then there's no problem getting it in. And that's a solution, but you know, obviously quite frequently you prefer it the other way around, so we could have come in and very quickly just lifted that up, and it's done all the loading cases. And if we then take this member here, we'll see we've got an apex connection here, and again we've got this problem with the spacing. And if we look at the dimensions, it'll tell us could be a problem. So very simply, on the top we'll just drop that to 100 down, and it's fine. And we'll just check that that's okay for all loading cases, and it's fine. Okay, what else have we got here? We've got a column, and we've got a column that is looking okay. Let's just scan it, and we find that it's actually a bit of a problem in loading case 46. Boys, I wouldn't like to have gone through those one at a time to find that. So what's the solution? We can ask the program, or we can do it ourselves. And the solution is really to go out to something a bit bigger, say a 300 by 300 base. Nice standard size. We still have a problem with the projections. So I'm going to take my bolts outside. I'm going to make this a 400 by 400 base, a standard size base, and everything now is happy. Well, actually the bolts are still inside, so probably I think the standard is 500 by 500. There we go. And you'd probably put those bolts to the corners. Edge distance, cross centers. Edge distance is 50. Cross centers will be probably at least 300. No, 400. So standard bolts, 50 in, 50 in. So 50 and 400. Now the beauty about this is we could come along at this point in time and say use this as the default for any more base plates. So I can specify my basic dimensions, I can specify my basic welds, I can specify my grout and concrete grades, which are very light at the minute and very small. I can specify whether I have mesh and things like that all automatically in this program. And I can do that for all the different types of joints. We also were looking at the simple connections. So if we look at here, we have a fin plate beam to beam and 179 kilonewtons. That's not going to cause much problems. We're probably way up. Well, we're up to 60% of our load. It's quite well in. And then we also have the same with a flexible end plate, which is probably more bolts, so therefore we've got a far lower utilization. So you can understand why the fin plate these days is becoming more popular. The same amount of welding, half the plate, half the bolts, for quite a few connections. And in this very competitive environment, that is important. What else have we got? We should have in here somewhere a beam to column. Here we go, beam to column. And if we put it into the column view, we will see again the notching of these beams as we expect. And it's the fin plate that's offset, so the beam comes in concentric on the design. And again, all your design checks are being catered for here. Even if you look at it, structural integrity check, so checking the bearing and tension. And if we go down to the column web side, we will see it's checking the structural integrity of that, and because we have it's also checking the column wall just to make sure everything's okay. So all your design checks there, straightforward and very simply done. So that's integrated design, that's standalone design, same program. So coming back, and I'll come back really to my previous example, I want to now to look at the fourth topic, the differences between the codes. So back out of here into my connections, and I'll just choose some SCI worked examples because it's easier to navigate. These are example files that were in the SCI worked green book. So eaves joints, what's the first thing that's different between the BS and the Eurocode? Well, the first thing, and I'm just going to switch this so that we see slightly smaller graphic but more of the results, that allows me to move about a lot easier. And I'll just turn off some of the symbols as well, so we can just see the basics, turn off all the dimensions, and we'll turn off our force diagram. So there's our basic joint. So first thing that's different is that we have now got circular and non-circular yield line patterns in our T-stubs for our connection. So bolt row, we end up with circular and non-circular. So we come down to bolt row 2, probably more common, and we'll see that we have our non-circular patterns, and bolt row 1 we have circular and non-circular patterns. So in mode 1 we choose both circular and non-circular. In mode 2 now we use non-circular only. So that's a major difference, not necessarily a big difference in results, but we're only using half the yield line patterns for the mode 2 failure where you have prying and failure. The next thing is that the bolt resistance formulas are slightly different to take into consideration the size of the head and the washer. So we will get slight differences in those formulas. The methods themselves are very similar, if unchanged. So it's a slight difference in yield line patterns, capacity is probably the same. The column web is considerably changed. We have this omega and we have this beta value. Now the omega and beta can turn out to cause you headaches, and it's really to do with the interaction of the column web on your connection. So that is going to give you a considerable difference, this omega value, in certain instances. Previously also we used a value of LT that was the effective length, which was based on 60°. Now it takes the effective length of the bolt row itself. Sounds strange. I'm not certain how I feel that, use is correct, but that is what they are stipulating. So we're doing it as required and ending up with a different capacity. The plastic distribution also has some slightly different conditions in that any bolt row resistance can go plastic when the bolt row resistance is less than 1.9 of the bolt tension capacity. Quite interesting. Strange, but quite interesting. You know, so you can have plastic, elastic, plastic. I'm not so certain I would feel that that's the way it should be going, but that's the way the Green Book is giving us this flexibility. And obviously it is based on research. Column web compression. Big change in this area. The effective lengths are the same. However, again, this omega factor is coming into play. So let's get down to column webs. So column web compression, we see this omega coming into play and giving us these strange values which give us a capacity in bearing of 817. The B effective has also been changed for the buckling and takes the 45-degree spread from the beam. That was how we did it in the old days. Now with the P398, we're using the same B effective as we did for crushing. So bearing and buckling use the same effective length, which means that you can have a reduced capacity. So if we take these values and we look at this and we say we are giving ourselves an 870 kilonewton load capacity here and 870. Oh, that's quite strange, but not really, because we use the same factor. What is it to the BS? And that's one of the nice things about our software, is we can switch between and have a look. So, whoa, bearing was, well, 860, but the buckling was 1172 to the British code. So buckling could have been a lot more enhanced in the BS, whereas to the Eurocode it has been throttled back, and in this case the bearing was more critical anyway, so it's not going to cause a difference. Beam compression is pretty similar, just takes a slight modification factor into consideration in the calculation of the moment capacity. The column web shear, we reckon it's about 12% less. The column web shear capacity, instead of being 0.6 as your normal modification on your PY, it's 0.9 of the square root of 3, which is 0.52. I don't know why they didn't say just 0.52, but they put it in as 0.9 over the square root of 3. However, most of this falls back into giving us our moment capacity pretty similar. Shear is another area that we have a big drop in our capacity in our columns in shear. When a bolt is in pure shear, that's fine. It takes all that capacity. But when a bolt is in shear and tension, we would have used the ratio of the shear and tension values over 1.4. Well, they've modified that, and if you look carefully, they've actually pulled it inside, and I think this is to do with it, pulled it inside the equation, so it's actually the shear over the shear capacity plus the tension over 1.4 the tension capacity. So it's only one of the two components now that's getting this 1.4 improvement, and that means that we are getting a 30% reduction in the shear capacity of bolts that are tension. So that's again another big problematic area. Another area that can be problematic, and not in this example because you don't have a haunch, is when we do have a haunch. Because we end up with a different set of rules for our hunched design. Now, do I have a hunched design? I thought I had a hunched connection. I don't. So I'll just nip back and open my other file. Yeah, that'll do. What we're seeing in our design is that we're actually having, previously we would have taken whatever we could down the web and whatever we could down the flange and design the welds accordingly, and just make sure that each of them could resist a quarter of the load, just to make sure you weren't applying all the force down one load path. Well, that wasn't even in the Green Book previously. The way they had it done was totally vague, and they just said, yeah, full size welds. And we came up with this method with discussions with the SCI. They've now gone one stage further, and they've said that you can have a limit to the amount of force you can apply to each of these. So basically 50% of the applied compression forces can be taken into the hunch flange. So it puts more onus on these two welds, and we find that we are beginning to find bigger welds. You couldn't say you got a nice long web, we'll take 75% down here and a quarter here. It says no, 50%. So you end up with larger welds here than you were expecting previously. We also are finding that we are finding larger compressive forces here being designed for with this weaker buckling capacity. So these are also resulting in stiffeners being applied here that weren't existing previously. The only other thing that is different, really, I'm trying to think, what is it? I've covered that. No, that's about it on the eaves connection, and the apex is the same. Now, one of the other things you'll notice with our input is that we have added the column shear and the hunch end moment. Now, if you remember, we were talking about our omega values, and any pre-existing shear across the connection has an effect. So we need to know what that is, and we will pull that during an integrated design. We also, I believe, in an integrated design have a reduction due to pre-existing moment in the column as well, and that cannot be applied in here directly. You would have to use the linked integrated design to account for that. So we are using the most onerous value for the design in that case as it stands. So moving forward, we're looking now at the other types of connections, the beam splices. The big difference in the beam splice is in the way the forces are dispersed. Previously we were allowed to, whoops, sorry about that, there we go. Let's just, sorry, my scrolling mouse, back here. I'll just click here to take it off the focus there. Previously we were allowed to specify where we could share the load, new moment in the flanges or in the web, and axial in the flanges in the web. That is now sort of cast in stone. And it's cast in the stone in that the moment is always shared between the flange and the web, and the axial is shared between the flanges and the web. The moment is proportional to inertia, that makes sense. The axial is proportional to area, and these can have a significant effect on your web. Now, the other thing that's considered also in these is the buckling of these cover plates. And finally, there's a new minimum check, resistance check of 0.25 of the capacity. Even if you've for a little moment in your beam, you still need to satisfy MED greater than 0.25 MRD. So you need to have a resistance that can resist those loads. Column splices, this is all done to the Simple Connections publication, and the main differences are again this minimum bearing capacity and also the buckling of cover plates. Even in a non-bearing column splice, you still have this 0.25 cover plate to satisfy the capacity of your cover plates and also the shear capacity of the web plates, very insignificantly 0.025 of the axial capacity of the weaker section against the shear capacity of the web cover plates. So there are some changes there. Now finally, hollow section, there's nothing really, no change there other than for the previous. Base plates is quite a big change. The big change in base plates, and let's get to a simpler base plate so we can just understand this easily, is in the calculation. Whoops, we just flicked the BS for a second there. We're back to Eurocode. That's better. And we find we're not working because I had twiddled with my load earlier in the morning. So let's look at our base plates. Concrete pressure. We have this thing called the pad diffusion ratio. The SCI default alpha is 1.5, and then the grout ratio BJ is 0.67, and the quick-minded of you will figure out that those two cancel each other out. So we end up with this FCD of 13, and for bearing we then apply this BJ and the alpha, and we end up with the same value for bearing. FCD, FJD is the same. But we can do better than that, because if we know that our base plate is onto a pad foundation that is, for example, 500 deep and is got an edge distance of 500, then we will see that the pad diffusion ratio has gone to 1.93, which means our bearing stress has suddenly jumped from 13 to 16.25. Now I did not take very ludicrous values there. I took a small 500 deep base plate, or sorry, pad foundation, and a 500 edge distance from the center edge of the plate out. And it's all to do with confinement of the concrete according to the concrete code. And it talks about it here, EC2662. But that does get you stronger compressive areas than we've had previously, which is great. And if you're into a huge big base, you can turn around and say, well, actually I have a meter. Makes no difference. What does make the difference is the combination of the two, but principally the depth. So if I went for 750 deep, I've now got a pad diffusion ratio of 2.2. So much better. And we've gone from 13 to just under 20. And if I made that 600, we might be up there. So if I made that 1500, I made that 800, we're up to 21, 22, so we're getting there. We're pushing it to its limits. Now there is an upper limit, thank goodness, of 300, or sorry, 3. I apologize there, upper limit of 3, but there's also a minimum of 1. So we can be in situations where we go below the SCI recommended values. And that's good, and that's correct, and that's the way it should be. When you have a column coming down onto a pad that's no more than a wall, you can't expect it to have the full compressive capacity because it's going to burst out early. So that would be one of the major things. It's a difference. The other major difference is the Y-line patterns. No longer must you keep this bolt inside this angle of 45 degrees. It can be wherever you want. And we will calculate the Y-line pattern for it. Again, like the A's and apex, this combined shear is also going to reduce your shear capacities by around 10% because of the 1.4 coming inside the shear component. Or no, inside the tension component, but not the shear component. Punching shear is a benefit because we no longer use 1.5L, we now use 2L. So that's going to give you a total increase in your perimeter of 4L. A half L round each corner on each side, so it's 4L. So that's another benefit for you in the base plates. So I will just sign off here and thank you all very, very much and say goodbye.